So a quick set of reminders, concept check 1A due this weekend, Sunday night. I guess I should also put that the muddiest point is due. I forgot to write that down. So add that in here, muddiest points. Point due Sunday. Good. So that too. Then otherwise, looking ahead, there will be this, so concentrate 1A, this is going to be mainly over this idea of drift and starting to think about drift applied to artificial populations you create in algorithms. So keep that in mind when answering those. A couple of short questions, and hopefully it won't take you very long to cover there. Muddy's point, for this week's topics. And then if you can look ahead, there is a concept check 1B and the mini project 1 they'll be doing in early February. 1B will be more comprehensive over and actually cover the evolutionary algorithms that we're going to start talking about the implementation of. And so that'll be more focused there. And the mini project 1 actually, that's the one that is not dropped, where it asks you to implement a simple genetic algorithm using whatever language you like, not using any GA off-the-shelf APIs that are already available, but instead you have to code up we'll talk about all the components of it. You have to code up your own chromosomes, you have to code up your own genes, you have to code up your own fitness function and selection operators, and it's for a relatively simple problem, and the implementation you make can be pretty compact. But that's something that we'll get into a little bit as we get sort of to the end of next week, and that'll become clearer on what those sorts of things will look like. I also add in here, this is kind of unrelated, not directly related to the class, but may be of interest to some of you, but today in LSC 202 at 3 p.m., there is a talk by Stephen Pratt. And it is on collective cognition in ant societies. So Stephen is sort of a world expert in ant and honeybee collective decision making. And this is on a certain type of ants that doesn't leave pheromone trails or anything like that, and they have to make discrete decisions. So you have to give them multiple discrete options, and then they as a group then choose the option, and what's the process that they go with that. It's a multi-alternative decision problem, so how do they trade off and all those sorts of things. So if you're interested in kind of distributed algorithms, and this is something that we'll get into when we start getting into kind of swarm intelligence, but kind of previewing that, if you're interested in hearing about real research that's going on in that, then today in the animal behavior seminar, 3 p.m. LSC, that's at 203, this is supposed to be 202. So then you can take a look at that. So, all right. So any questions about assignments or admin stuff moving forward? It feels darker in here for some reason. Okay, so we've been talking about how evolution is the change in allele distribution in a population over time. In a genetic algorithm, as we start to define how to write a genetic algorithm, then the allele distribution, we'll view that as the strategy distribution. So if you've got 100 candidate strategies, some of those strategies might use a variable in this range, a temperature, a hot temperature, or a cold temperature in a chemical process. Might use a high weight at this synapse between two neurons in a neural network, or a low weight, and so on. So evolution describes how these strategies change in distribution. Does everyone have a high weight at that spot in the neural network? Do only a few have a high weight in that spot in the neural network? And so evolution is saying that these distributions are changing. So the use of strategies is changing in proportion over time. And evolutionary algorithms harness that by reshaping a population of potential candidate solutions based on relative success. So you have 100 candidate solutions, you try them 100 times in your optimization objective or your simulated version of the system, and you get 100 performance metrics out based on the relative performance there. So this one does a lot better than that one. Then you're going to say, I'm going to investigate solutions that look a lot more like this one than that one. So when you end up mutating your strategies, you might have a lot more mutants generated of the high-performing one, which will kind of more exploit that region of the strategy space than the low-performing one. So that we, as we start implementing the GA, that we see what mechanisms we put into code that make that happen. And so right now we've been setting up the foundations for understanding the language of that and where these tools come from. So it's basically an intelligent trial and error process with multiple trials in parallel. That's what an EA is. Okay, so last time we started then talking about the 4 forces of evolution. So we are going to use these forces to shape our candidate solutions. So we start out with just random guesses of we think this is a good neural network, we have no idea. These are 100 different neural network configurations. These are 100 different ways that we could configure the joints in this robotic system we're building, and so on and so forth. And so we have those there, and this approach uses the forces of evolution to reshape that population, to move it from a random set of designs hopefully into a new set of designs. That's going to require both discovery, exploration, and tuning, exploitation. So when we talk about mechanisms that add genotypic diversity, what we're saying is mechanisms that explore new solutions, new candidate solutions, strategies that you've not tried before. And so mutation is the key way that we introduce those new strategies. And so we'll see how mutation is implemented in the GA as we start writing out the implementation for the GA. But in a nutshell, if a gene is a variable in your candidate vector, in your vector of things you can do in your solution, then simply randomizing at that location is a way to mutate. So if you say I've got one weight in my neural network that is 0.5 right now, if I decide to target that with mutation, then maybe I add some random noise to it, so then it becomes 0.7 for one mutant, 0.3 for another mutant, and then I retry, and I see if that exploration has improved or reduced my performance based on what the parent had. So that's one way to introduce, and this is the way we're going to focus on in this first unit. And a couple units down, we're going to start talking about distributed genetic algorithms, where we actually do implement the genetic algorithm in a more parallel way, where instead of thinking it as one population that's constantly mixing with each other, we can think of it as a little genetic algorithm, another little genetic algorithm, another little genetic algorithm that periodically exchange. And that allows us to start thinking about migration. And it turns out that by creating these subsets of genetic algorithms, it can introduce, new ways to vary these populations. And so by isolating populations temporarily, you allow them to kind of take on, move into new spaces that if they were kind of subject to the peer pressure of being in a giant group, they may not be able to divide and conquer. But if you keep them divided, then you allow these populations to run off on their own, but then they periodically share the things that they found. And that can make for a very different dynamic for how you search through these solution spaces. So that's what we'll get to when we get to distributed genetic algorithms, which will be the little more advanced topic. But for a while, we're just going to be focusing on mutation as our way to get new solutions into the space. So as I was kind of hinting before, increases in, I'm going to use the term genotypic diversity. So these by themselves do not imply that we have better function, but you need more genotypic diversity. So you need more diversity in strategies you're trying just to give you the option for phenotypic diversity. So you need more differences in how you configure the machine to get different machine behaviors. And then from those different machine behaviors, you might get differences in fitness. So if I've configured my robot, I've got 100 different robots, they all have different springiness of their legs, and then I want to see which robot climbs up the stairs. Well, if I had them all with one spring tension of their legs, then it might be that certain heights of the stairs they're well suited for, but if I try generic stairs, the robot can't climb those stairs. So I build a couple of robots that have little slightly different springs, so maybe they have a little more give to them. Another that has stiffer springs. And then I try this population of these 3 different spring constants to see if I can climb up these stairs more efficiently with them. So I need a genotypic diversity, which is the different spring constants, to give me different phenotypic diversity, which is the different ways they manage to climb the stairs. So it might be that if you have a really stiff spring, then you might be able to skip some steps. But as you're skipping those steps, you might also fall over more often. So just because you're climbing the stairs differently doesn't mean you're climbing the stairs better. So you might have a lot of genotypic diversity and a lot of phenotypic diversity, but it might mean that all the solutions get up the stairs roughly the same amount of time. So if you're minimizing the time it takes to climb up the stairs, that's your fitness function. But the only way you're going to get differences in fitness is to have differences in phenotype. The only way you're going to get differences in phenotype is to have differences in genotype. Now that's assuming the same environment. So I mentioned that phenotype is it emerges from the combination of genes and the environment, G by E, what we say to that. Well, of course, if I change the stairs, that's another way to get different phenotypes out. So, we talk about design for manufacturing. So some people design humanoid robots because our world is sort of built for humanoids, built for us. And so if you want the robot to be able to open doors, it should be able to grab a doorknob. If you want to be able to drive cars, it should be able to grab a steering wheel and so on. If you want a robot to be able to pick tomatoes, then it may need to be able to put its arm anywhere and grab any tomato and have sort of a soft touch and so on and so forth. Now, an alternative is design for robotics. So in that case, you could say, well, the robots, we're going to guarantee that we design the environment, so there might be a weird environment for humans, but it's really ideal for robots. So I know a guy in Las Vegas who designs different lighting schedules for indoor agriculture. And so he controls where the tomatoes will emerge on the tomato plant by changing the lighting around the tomato to drive the tomatoes so that hopefully all the tomatoes always come out at a certain height. If you can control where the tomatoes are, then now you can have a dumb robot that just has a machete or something and slide it and then they all drop. And so you don't need to have an arm that is able to navigate in computer vision to figure out where the tomato is. So that's an example of designing for the robot. So the robot that is just the machete might be terrible out in the field, but in that in that environment, that indoor environment where they control how the tomatoes grow, it has very high fitness. So and it just looks different. So phenotype emerges from your strategy and also the environment you put the strategy into. So when we engineer things, sometimes we think about am I thinking about this backwards? Do I really need to build the best robot ever? Or can I build an okay robot and make some assumptions about the environment around it? And I think a lot of nature is embedded in the environment around it. So there aren't a lot of general purpose. There's no ants that can do your taxes, but there's ants that are really good at telling the difference between a dark cavity and a light cavity. And so they're good at certain problems, and they make use of dynamics that they get from the environment around them. And that's something that we often, as engineers, we want to make our systems robust to the environment so they work in every environment. But that makes for very slow and very expensive designs. So if you can make some assumptions about the environment, you can often make your designs cheaper. So G by E is what we're sort of talking about there. All right, that's how we introduce diversity. Any questions about that? So this is we're going to eventually drill down into how to build mutation operators. and make all this work. But for now, I just want you to know that these are the two ways we introduce diversity: mutation and migration, and we'll get more into migration in a couple of units when we talk about distributed genetic algorithms. All right, so the big thing we want to focus on then is making sure we understand these two important pressures of drift and selection. And so introduced this last time. This is how these are both things that decrease genotypic diversity. So you take a bunch of diverse strategies, and after they've gone through drift or they've gone through selection, you have less strategies, less diverse strategies when you come out. So hopefully, if we design things well, you have a greater proportion of the good performing strategies, and the really poor performing strategies, the good ones have taken their place. That's the hope. But there can be forces like genetic drift where you're going to get that reduction in diversity, but it's random, sort of who's the winner. So that's random chance removal of individuals that is uncorrelated with their phenotype, or bad luck. That's basically what drift is. So the conceptual process is, imagine I start with n individuals. Later in these notes, I use capital N. It's the same here. So n is my population size. And let's say all of these individuals have equal fitness. And so we'll talk about natural selection here in a second, but fitness is just the number of offspring an individual has, is their fitness. So if all of them are equally fit, then they'll all have F offspring. So after population growth, we'll go from N individuals to F times N individuals. So these F by N individuals. And that's just everybody grows. Everybody gets 2 offspring. So if F is equal to 2, let's say here, then this would be equal to 2N, and you get to a doubling of the population. But in reality, in natural systems, you just can't grow populations that way. You run out of resources. In our evolutionary algorithms, we typically do not allow for changing the population size dynamically over the algorithm. We only have enough spots in our array for n individuals. So we might temporarily be able to expand them, but at the end of the iteration, the invariant that must be met is that we have n individuals going out before we start the iteration again. So there has to be some reduction back down to this n. And we can think of that as a resource limitation. So in natural systems, you can think of it like a carrying capacity. There's only so much food available, so you end up reducing things down to n. And this is basically random mortality. It is mortality that does not depend on the phenotype. Anybody can get hit by it, regardless of what genotype and what phenotype they express. So the idea here is, well, let's think about if we had 3 different strategies that all were equally fit. So we had, again, if we're optimizing for speed of a car, the color probably doesn't matter. So this is the number of red cars, the number of blue cars, the number of green cars. In cars total, but we divide up and it's just how many colors are there. And we might start out with an equal number of each. But if our fitness function is the speed of that car, color probably doesn't have any effect on speed, so they're equally fit. So as long as everything else is the same, they're going to be equally fit cars. So the question is, if we start out with a certain mixture of colors, and we go through this process over and over again, is that mixture maintained? Do we maintain the color diversity despite it being a neutral trait? And so if we think about that process, then we start out with this mixture. So this you can think of as number of red cars, blue cars, green cars, if you wish. Every car, gets F individuals potentially in the next generation. So now we have F in A, red cars, F in B, green cars, F in C, blue cars, whichever ordering I did the colors there to begin with. But we only have room in our genetic algorithm to keep track of n of them. So we have to randomly reduce that down. So now we have a big urn that has F times n individuals in it, and we're just going to reach into that urn blindfolded and just grab out in individuals out of the urn. Now we don't, we can't look down in, we can't make sure that we're grabbing, one red, one blue, one green. We're not, it's just randomly reducing the population back down to N. So we get a new number of red, a new number of green, and a new number of blue. Yep.
How do we say that the randomness is truly random here for mortality? If you were looking at a system, how would you say there was no alleles or any like genetic superiority over other population?
Well, so in some ways, this is the ideal case. We know that even if there's a slight bias that for some reason, maybe the red paint feels a little bit different on the fingers that are reaching into this urn to grab the ball out that's red, that maybe there's a slight, there's some slight variance that could be explained by the texture of the paint or something, but most of it, we're saying here is explained by randomness or unexplained variance. And so likewise, if there's a population of, dinosaurs and a meteor hits the Earth, then there's going to be, that's likely going to kill a bunch of dinosaurs, regardless of if they're big dinosaurs or small dinosaurs, or else they have wings and so on. And so there will be some that survive, but if you survive, it's just due to luck. You happen to be sheltered at that point. You happen to be underground when it hit. So your phenotype, if you're always underground, if you live underground, then that's going to give you an advantage for sure. But if we're just focusing on the general case where you might be underground, you might be above ground, and when that thing hits, then it's basically a random chance if you survive. Likewise, if something hit this building, it doesn't matter who's in the building, everybody in the building suffers. Yeah.
So what happens if, for example, we have groups with two different fitness? This drift only happens to the group with the lower fitness?
Yeah, it's a great question. So right now we're focusing on the neutral case. So, and so why does that matter? Because as we'll get into, I mentioned that drift decreases genotypic diversity, so does selection. So initially you might have a really high performing group and a really low performing group. In the next generation, the high performing group is going to produce more offspring than the low performing group. So what's going to happen is in the next generation, most of the individuals will be high performing and you have very few low performing. Eventually, you'll get all high performing individuals. At that point, natural selection leads to neutrality because now you've got 100 individuals that are relatively similar in fitness. And the real question is, and this is what we're going to answer here, this is a so-called drift barrier that was kind of going to be the punchline of this whole thing, is how much better does a phenotype need to be to guarantee that it is stronger than drift? So to put that another way, if we know that there's a rate of random mortality that kills one individual per day, it just randomly one individual per day dies, doesn't know, who it is. It's kind of there's nothing to do with that particular, it's just totally random. Then you have to say, okay, or per generation, maybe that's an easier thing. If one individual dies per generation totally randomly, then in order for fitness to be stronger than that effect, then you better be producing enough new offspring to be able to compensate for that rate of random mortality. Because if, let's say there's 4 individuals and there's a random mortality of, one individual, that's a huge section of the population. So if fitness is only going to change that distribution fractionally, so it's going to take 100 generations for the slightly better fit individual A, like A, B, C, and D. And individual A is a little better off than individual B. Well, at this small population size, that little better off might mean that on average, after 100 generations, A will finally displace B and you'll get AA, CD or something. So only then will its advantage kind of show up. Well, if it takes that long for selection to cause an expansion of the slightly better strategy, it's much more likely that drift is going to knock out maybe A entirely in between there. So the question is, if we have an idea of like this random reduction here, this puts a pressure. This basically is going to set a barrier where your fitness differences is going to need to be greater than some barrier in order to survive this random chance. And what we'll see, and this is kind of hidden down here, but what we'll see is that in large populations, like if you have millions of individuals, the drift barrier is very, very low. And it's very easy because you won't eliminate individuals. You won't eliminate whole strategies through a little random mortality. But in small populations, which ideally, computationally, we like to have small populations. I don't want to be keeping track of a million alternatives, like brute forcing my way through the decision space. I'd like to keep track of maybe 10 at a time. But if I have a really small population size and I keep going from 10 to 30 back down to 10, that random reduction is going to have a very strong impact on my allele distribution without fitness even coming into play, without selection even coming into play. So that means that I may need to increase my population size in order to get a better signal to noise ratio. That's what this is going to come down to. This is noise, selection is signal. The smaller your population size, the bigger the noise. The bigger the population size, the bigger the signal, or the smaller the noise. So in order to be able to find the signal of high quality solutions, you need a good signal to noise ratio. And that's what we're going to talk about here. Again, the punchline of this is going to be the so-called drift barrier, which gives us this idea what the signal to noise ratio is. Okay. So then, kind of hinted at some of these things. So the key things here is that if you start out with an equal distribution of neutral types, like so the neutral trait, and they're just equally distributed among all those, then you can say, well, how likely, if they started out balanced, so everybody's got the same amount, same number of red, same number of green, same number of blue, how likely is it after this random reduction that they stay balanced? And it turns out that there are more unbalanced distributions than balanced distributions. There's only one numbers, like if I have 30 individuals, and then it'd be 10, 10, and 10. That's the only way I can have things equally distributed here. Anything else is going to give one of the other ones a slight advantage. So just through, you can think of it through entropy, then it's going to be that if you start equal, it is very unlikely you're going to end equal. So that equal is going to be sort of an unstable state. So then the question is, let's think about these unequal distributions. Well, without going through all the math, those of you who had some practice working with Markov chains could write out a Markov chain for this, where you keep track of, you've got these, they're just counts. So all of these always had to add up to 30. And so you have basically a random transition from different discrete states. So you might say you start in a 10, 10, 10, and there's a certain probability that this random mortality is going to bring you to a 10, 11, 9. There's a certain probability it can bring you from a 10, 12, 8, so on and so forth. So you can set up transition probabilities from these demographic counts to every other demographic count. And then we can sort of think about what that Markov chain would look like. One of the things you'll find is that if you start with one of these compartments having a majority, there will be more opportunities to further increase that majority than decrease that majority. And this basically comes down to this idea that, like if I had 99 red cars, and maybe I'll do 98 red cars, 1 blue car, 1 green car. And then I go through this fitness expansion and then this reduction back down to 100. Then you could say, well, there are, I'm basically going to draw from this urn. And every time I draw, it's very likely I'm going to get one of the red cars that is in that huge majority. And so maybe I went a little too much to the extreme. I said 99, 1, and 1. But if this was like, 80, 10, and 10, then we're going to find that it's very unlikely that these are going to get lucky enough that they're going to end up adding up to more than the 20 that they started with. So you get a rich get richer thing here, is that when you randomly draw into the urn, any majorities that are in the urn to start with are going to bias the selection of the random population on the output, so that those majorities are more likely to be maintained than lost. So once you start moving toward red, you're going to stay moving toward red. And then once an allele loses its count, it hits a count of 0, it can't come back. Because once you're not in the population, it doesn't matter what your fitness is. You have no individuals to reproduce, so you can't produce any more individuals. So at the point where you lose your green cars or your green solutions, you lost them forever. They're not coming back. So now you just have red, which has a huge majority, and whatever the green, the blue, or whatever the other color was, it might have a few. But if there's like 98 red and 2 blue, and this random mortality tends to, is strong enough, then there's a very good chance that you're going to lose all of those blue. And once all of those blue are gone and all those green are gone and all those are red, then now you've reached a stable state. So the absorbing state of this Markov chain is when you're just dominated by one neutral strategy, one neutral trait. So all red, all green, and all blue, those are the 3 absorbing states of this Markov chain. Once you hit them, you're stuck there forever in drift without mutation coming in and adding diversity. Yep.
Is that a good thing or a bad thing?
It's a bad. I would claim that drift is something that is, when we get to distributed genetic algorithms, we will learn a way to turn this into a good thing. But for now, when we have a single population, this is a bad thing, because we, at least from an engineering perspective, nature is not necessarily optimizing, but we are optimizing. From an optimization perspective, we're losing strategies regardless of what their fitness are. That's a bad thing. So we want to maintain genotypic diversity as long as possible. Now, I mentioned drift reduces genotypic diversity, gets rid of strategies. So does selection. So we can have a similar problem if we have an overly excited, we can have the equivalent of a greedy algorithm in natural selection, where it can get exuberantly excited about one strategy that happens to be a little more fit than the others, and it can then flood the population with that one strategy and never explore farther away in the space where there might have been a better strategy. So in general, reductions of genotypic diversity are a bad thing. We would like to search, we'd like to keep the good solutions we found while maintaining as much diversity as possible. That's going to be a common theme for genetic algorithms or genetic algorithms adjacent to a genetic algorithms. If they work really well, they do those 2 things. They keep the good things they found, and they maintain diversity in everything else. Okay. Questions about any of this dynamic? I think I sort of go over this in a little more, so this is abstracting the same story I was just telling you. So this is borrowing from game theory, this notation. So imagine this is an arbitrary vector where this is the number of individuals with trait X, and this is sort of saying every other trait. So n minus X, that's the count of individuals with any other trait. So, that's what this notation here. So I'm just saying that once one individual is the entire population, once nx is equal to n, that's what it says there. So all the same allele. Then if you go through the fitness process to reproduce, reproduction still, you just get a bigger population where they all have the same strategy and nobody else has anything else. And then when you reduce back down, then you look exactly like you started. So that is a stable absorbing state here. So biologists refer to this as fixation. So we will say that something drifts to fixation. So biologists will say when they're describing the history of a population, they'll say we see evidence that this strategy was stronger than these other strategies, so gradually they beat them out, and then eventually there was a little bit of residual variance left over, but the fitness differences weren't that different, so we ended up just drifting to fixation, meaning that one of those strategies that were very similar took over, but it took over not because it was the stronger strategy, but because the drift was stronger than selection, and you just arbitrarily got one of them being selected. That's just the absorbing state of a neutral Markov chain. So the allele with larger numbers is more likely to fix. So if you start with a population where you've got a bunch of different alleles, but one of them has a huge numbers advantage, if they're all of similar fitness, that's the one that's more likely to drift to fixation. The characteristic time to absorption, fixation of this Markov chain, is proportional to the population size. So it's on the order of n, where n is our population size. So I've been calling that n above, so lowercase n. So, and that will become important when we talk about the drift barrier here in a second. So basically, the number of generations it takes for you to hit fixation is proportional to the number of individuals in the population. So if you make your populations larger, they take longer to fix. So drift is slower in larger populations. The effects of drift scale inversely with population size. So when you're coming up with your hyperparameters for your genetic algorithm, then you'd say, well, why would I want to pick a larger population size? What's the advantage of a larger population size? And the advantage is that you can fine-tune more precisely because you will be more sensitive to small differences in fitness. You're basically making this drift force smaller and smaller. So if you're just looking for a coarse-grained best strategy, you can use a small population size. It'll kind of do a heuristic search. It'll find something that's good enough. There's probably other things that could be, you could probably fine-tune that strategy. So maybe you've got another way to fine-tune parameters and you just need to get in the ballpark and then you're going to toss it off to another algorithm, some PID tuning heuristic that you learned or something like that. Well, then maybe that's fine. Use a small population size here. But if you want the GA to do the tuning for you, you're going to need a large population size. So now I'm just trying to give you an intuition as to where the population size hyperparameter comes from. Most of you, when you talked about hyperparameters, you might have only experienced with things like step size, and learning rate, and you have some intuition on how to use those. This is how we're building intuition on how to use these hyperparameters. We think about it in terms of drift. And so there are neutral theories of evolution that apply. There's a bunch of contexts, particularly in molecular evolution, where we think that the traits have very, very similar fitness. So at some point, there's either the population sizes, the effective population sizes are really small, or there's just not that much fitness difference, but there's a lot of opportunity for genotypic difference. And so there's these so-called neutral theories of evolution that combine drift with mutation. So they basically say when selection's not happening, but the other things are, then what you find is drift is going to keep driving a population to one of these neutral traits. But then mutation will end up adding in a little more variation, and then drift will then take over again. And so these neutral theories of evolution help to explain diverse patterns in phenotype that you see in nature that may have nothing to do with fitness difference. So some people have scaled these up from the molecular realm into thinking about more macroscopic things. Like there might be some aspects of a forest canopy where it turns out that there are some aspects of that, the way those trees look, that really don't give them any better ability to gather light from the sun. And because they're constantly mutating, coming up with slightly different variations, but those variations are neutral relative to the others, then you've constantly got drift purging that variation, and mutation reintroducing it, and they can kind of come up with a balance. And you can end up explaining these patterns, not because you can say, well, these two strategies are one's better than the other. You can say, well, actually what you're seeing here is variation that's being managed by these two forces that have nothing to do with fitness. So that's kind of an aside, these neutral theories of evolution, but just know that if you combine neutrality with mutation, which is effectively what happens after selection has been running for a while, eventually if you're at the top of a fitness peak, your optimization objective is pretty close to being optimized. The only things really left over that are running things are mutation and drift. So you may see diversity in your populations that are being spit out of your algorithms, but that diversity doesn't mean that real work is going on. That diversity might just be churn from drift purging diversity and mutation re-adding it and then getting purged and being re-added, a dynamic equilibrium. Yep.
Can you give a simple example of how a Markov chain model would look like in this case? Like what would be the individual states? What would define the transition probabilities?
Yeah.
Or like would it be discrete continuous?
Right. So like the kind of Markov chain here, you can think of this as a discrete, there's discrete states, which are the counts of the different trait values. So in general, this would look like, if I had a state might look like, this would be like the count. So I'm going to say the count of, maybe I'll put a little number. So I was thinking like, sometimes chemists like to use this for counts, like the count of A, the count of B, and the count of C. So let's say there's 3 trait values here, A, B, and C. And I'll also just write that as instead maybe the number of A, the number of B, and the number of C. So an example might be you've got a state down here that is 5, 2, and 3. And there might be some invariant that the number of A plus the number of B plus the number of C is equal to 10. So then you could say, all right, let's say I go through a generation, that includes both, everybody gets their reproduction, and then you get reduced back down to 10. Then you could say, what are the states that are accessible from here? And so you could say, well, it could be that nothing happens. So in that case, you got an expansion and then go right back to it. Or it might mean that A gained 1, and that means that somebody else had to lose 1. So then there would be a state transition probability to another state up here where we've got like 6, 1, and 3. And then we might alternatively have another 6 option that might be 6, 2, and 2. And so there's going to be some probability of each one of those. So if you knew, or if you modeled this aspects of this random mortality, then you could model what is the probability that this is going to happen. So, so what we'll typically do in the GA is we're not going to you can't implement a GA this way, but you typically don't create a transient population that's larger. Like you don't just take this vector of, you might have complex data structures. Every individual, the genotype of every individual, the genome of individual might be this ugly data structure that you don't just want to create a bunch of them just to throw away. So instead, we'll use probability. We'll basically say, based on your fitness, what's the probability that you're going to survive? Now, the funny thing about probability, so if you make probability proportional to fitness, then in this case, you're going to tend to provide, then individuals in the next generation will tend to be higher fitness individuals. But there's always a chance, even with a coin that's 90% heads, tails will come up. So that is the act of drift. So the upper side of it, like the the proportionality here, that is selection. But the probability is drift. And you could argue that making this probable like this, or making this a probabilistic operator actually gives you a little bit of exploration, and we'll get into all of that. But my point I'm getting here is if we do this, it makes it much easier to do this. Because now we can say that if we know the fitness of this individual, it has a fitness F, then we'll be able to write out the probability of this transition given the fitness from the previous state. So we'll be able to say here, what's the probability that this one gained? Well, we could say, well, okay, so that would mean that of my 10 individuals, I know that there was a certain probability that each spot was populated by trait A based on the probability that, based on the fitness of A, I can get the probability that A gets a spot in the next generation. So I could do that for all 10 of my spots. And then I theoretically could then figure out what's the probability that I go from, that I get an increase of 1 in A, and so on and so forth. So it's a little ugly, but in principle, you can write this chain out. Does that make sense? And the point I'm getting to here is all of these are going to be transient states. There will then be this absorbing states, which will be when, once you get zeros here, once you 10, 0, 0, 0, 10, 0, 0, 0, 10, at that point, you're always going to get self loops. Okay. Any questions about that? All right, okay, so natural selection. So we're going to come back to that markup chain process in a second, but we have to talk about natural selection, and then we can talk about how the two are balanced against each other. So natural selection, differences in fitness lead to changes in proportion, relative proportion of alleles. So I'm emphasizing here differences in fitness. Every individual might reproduce, but some reproduce more than others. That's what reshapes the populations. So with that, we've got every individual's got a fitness. You can think of this as the number of offspring for that individual. And then we can talk about the average fitness of all individuals. So that's the average number of offspring. This is the growth rate of the population if you didn't limit their size. So if some individuals have 1 offspring, some individuals have 5 offspring, then overall you might say the population has got 3 offspring. And so the population triples in size every generation. But within that, some individuals are reproducing more than others. And so even though the population is increasing, the proportions are changing within that increasing population. So what we're really interested in is how the fitness of an individual or of an allele varies or differs relative to the average. And that is the so-called selection coefficient. So a selection coefficient, again, it's just, here's for this individual or this allele, this is how much that allele is reproducing. This is how much the average reproduction rate is from the population. We normalize it by the average, and so we get this selection coefficient, which is sort of an amount of bias in the expected reproductive success. So if everybody had equal fitness, there'd be no bias. You just have a population that is maintaining its proportions. But once you have a selection coefficient that is greater than 0, then that means that you have an individual that is reproducing more than the average individual. And so that individual will tend to have more representation in the next generation, so-called selection bias. So you can think of this as 20% more offspring than average. So selection bias 0 is the neutral case, negative, you're declining over time, positive, you're growing. And then from there, this is a term that we'll use a lot in our evolutionary algorithms, is selective pressure. So selective pressure is the effectiveness with which these selection coefficients change the population composition in the presence of drift. What I mean by that is this is basically, I think I'd say this here, is here. So if you have a high fitness diversity, you will have high selective pressure. What I mean by that is if you've got some individuals that are really, really fit relative to other individuals, so a huge diversity in fitness, then you will have the maximal amount of reshaping of the population. So in other words, that individual, because there's an individual way at the bottom, the individual way at the top is going to have a huge selection coefficient, which means in the next generation, you're going to see a lot more of those individuals that look like the individual at the top, and you may not see any of the individuals that look like the individual at the bottom. And that's what I mean by high selective pressure. So from an EA, when we write out the GA next time, we'll see this. But when you start with an optimization objective, you're going to choose a mapping to fitness. And so that fitness, that choice of optimization objective to fitness mapping helps tune your selective pressure. So what you're saying is, how much do you care about a very small increase in fitness? So or I guess I'd say a very small improvement in your optimization objective. So if your optimization objective, you're trying to minimize some curve. So you've got some curve over here that you're trying to minimize. This is your f of x that you're trying to minimize. And so, and you've got a candidate solution here and a candidate solution a little bit smaller, farther down than that. You're going to have to create a fitness mapping that that is going to want to make the one that's closer to the bottom higher fitness. But how much higher fitness? If you create a scaling so that being very close to the bottom as you have huge fitness and being right next to it is very low fitness, and that's referred to as having high selective pressure, because it will sort of guarantee that this one that's close to the bottom is going to dominate like in the next generation. But you could alternatively say that once that you get kind of a square root mapping from improvements in your optimization objective to fitness. And so if it's a small improvement, maybe it's got a very small fitness difference, and that will be less selective pressure. Now you might say, why would I ever want less selective pressure? But this goes back to what I was talking about earlier. If you have high selective pressure, you're going to deplete your genetic diversity super fast through selection. And that might be good for this peak, because that means you're going to find this bottom point here. But let's just say that there happened to be another peak that's even lower out here that you just haven't explored. If you purge all of your diversity so that everyone stays here, then there's no chance that you're ever going to have individuals that are left over that go over here. Like you might have had another individual that was sitting up here just waiting to explore. With a little bit of mutation, it could have hopped over that hill and then went down through there and found this one. But if you have high selective pressure, then when you look at these three individuals, it's going to kill this individual, and it might even kill this individual. So you're going to get a bunch of offspring that look like this individual. And that's really good for fine-tuning this local trough. But if you really wanted to minimize globally, you wanted to have an individual that stays walking around so it could find this one. So when we're designing our hyperparameters for our genetic algorithm, we worry about population size. That affects drift. We also worry about selective pressure. So we need to be careful what our mapping to fitness is, because if we make a too strong mapping to fitness, then once you find one slightly good option, your whole population will just suck to it, and then you'll lose all your exploration. So that's why we talk about selective pressure. Yeah.
Why not just keep like a minimum population for a strategy, basically?
Well, there are diversity preservation mechanisms that we're going to be talking about, particularly as we get to multi-objective optimization, because there it's really important because you've got multiple fitness functions. And so if you find a strategy that minimizes one fitness function, you might deplete all of your population that are checking out the others. So there are diversity preservation mechanisms that effectively reduce selective pressure And some of them work in a way like you're saying, like they kind of put safeguards on making sure they might introduce like higher mutation, but in a more targeted and infrequent way. So occasionally, if you just they might and there are other optimization approaches that aren't nature inspired that have this idea of resets. So if you happen to notice that all of your points converge onto some spot, we've talked about you might terminate your algorithm once there's no diversity left in your individuals here. An alternative is if you still got the computational budget, take half of them and randomly scatter them around the population, and then restart your algorithm. So resets and restarts, that's an option for that, and that will also help preserve your diversity. But all of these approaches effectively reduce your selective pressure. So diversity maintenance, low selective pressure, rapid convergence, high selective pressure. So trade-off. Questions about what I mean by here, selective pressure? This will become clearer as we start implementing the GA as well, and as you sort of play around with these different fitness options. Okay, so let's connect selection and drift. It's a kind of a punchline here. Now this is a heuristic, approximate, simplified explanation. The real explanation here, we'd have to talk about drift diffusion processes and how these two forces balance. And when you model selection and drift with a drift diffusion process, as the population geneticists like to do, there's this frustrating thing that drift becomes diffusion and selection becomes drift in the drift diffusion model. So there's just a bunch of complications that are outside of the scope of this class, but happy to talk about offline. So this is my kind of heuristic as to explaining the drift barrier without that. So drift will reach fixation in on the order of n generations, where n is your population size. We said that earlier. So that's how much time selection has to act before drift takes over. If selection can't make an impact on the allelic distribution, if you can't get evolution by selection in n generations, then selection is cooked. You're going to have pure neutrality. So the idea here is to think, now we've introduced that selection coefficient. That selection coefficient is like an interest rate at the bank. So the idea here is an allele with a selection coefficient S. So remember, that's the extra percentage you get relative to average. It will grow by 1 plus S to the n. That's the compound interest formula from the bank. So S is your interest rate from your selection bank. N is the number of generations, the number of compounding periods you have in order to make any money. If you can't make a critical amount of money in those n periods, then basically your account gets zeroed out. It's like selection isn't there. It may as well be a zero interest rate. So this is a key quantity we're going to look at here. So for selection to be distinguishable from neutrality, then I'm going to say, I'm wondering how big does selection have to be? So what I really am okay with is selection coefficients being small, because I'm saying if at some point my small selection coefficient is big enough that it will overcome drift. So this compound interest formula, if I consider S to be small, I can approximate it by this right here. That's just one of these approximations for this formula here. And so this becomes our growth, and I could say that, I'll just say here that S is small. That's our approximation that allows us to do that. Okay, so this goes back to signal to noise. So what I'm saying here is that it turns out, and again, the full description here requires me to go into drift diffusion processes to talk about variance and how much variance you get from drift, and sort of what's the mean effect from selection. And so I'm hand waving over all of that and basically saying over this n period here, drift will have effectively a constant effect on noise added to the population, whereas selection will have a linear effect relative to the size of the population. So if you have a big population and selection is active, then you can get more bang out of your selective buck. Regardless of your population size, drift kind of has a constant effect on the noise it's adding to the population distribution. So, so this here, you want this growth, this compound interest formula, to be much greater than a constant. So that's what on the order of 1 basically means, much greater to some constant. And what this will lead us to, if you look at this, well, this is just a constant plus n of s. What this is going to say is the product of your population size and your selection coefficient must be much greater on the order of, it must be bigger than a constant. And I'm not specifying what that constant is. And so that gives us this so-called drift barrier. And so so this is a hand-wavy explanation of how we got here. If you actually want to see where this comes from, it requires a little bit more sophisticated math to describe this drift diffusion process. But it comes down to the same result, that if your selection coefficient is bigger than 1 over n, where n is your effective population size, the number of reproducers in your population, then selection will dominate drift. Otherwise, if your selection coefficient is less than 1 over your population size, drift dominates and selection doesn't make an impact. The so-called drift barrier. The drift barrier was invented or was discovered in about 2010 by a guy named Mike Lynch, who since then has started at ASU, who works at biodesign right down the street. Really influential guy, done a lot of amazing things in his career, and this is one of them, the so-called drift barrier. So, so we know that S, the selection coefficient, declines over time because genotypic diversity is purged through selection. So if you have a lot of selective pressure, you will get a less diverse population later, which will give you less selective pressure. And so S will decline over time, which means you eventually will hit the drift barrier. You'll eventually have a population where selection basically turns off, and all you're left with is evolution due to drift and mutation. That's the sort of lesson here. And so and that's unfortunate because that's just where, like, you found the region of the decision space where your solution is likely to be, and you'd like to fine tune that solution. Now that you're like, okay, we know that I need to have roughly, I need to have 4 wheels on the car. I don't quite know where those wheels should be. They should be farther out or they should be in, or whatever, those sorts of things. I don't quite know the size of the wheels, but I know that a 4-wheeled car is much better than all other configurations. You found that spot, and now you'd like to fine tune. Well, if you only have 4 individuals in your population, then you basically lose the ability to fine tune. Because that 1 over 4 is so large that if the differences in fitness aren't different enough to get over that 1 over 4, then you will get different vehicles each generation if you've got mutation there, but they'll be random. So that's what big population sizes give you, is the ability to fine tune and not just be getting random changes in your configurations. That's the drift barrier. Questions about what I mean by that? Yeah.
So selection is, you have, say, a red marble. Its children will be the next generation, and with mutation, they may become blue marble and red marble.
We'll say pink or crimson, something like that. Yes.
Pink or red.
Yeah.
And drift will be which one of them survives the say population size 1.
Right. So it's like red becomes pink, red, crimson. That's selection with mutation. Drift is arbitrarily only one of those can survive. So maybe it's the pink, maybe it's the red, maybe it's the crimson. Questions about that? So if we put all of that together, we start getting a trajectory that looks like this. So we've got our effectiveness of our evolutionary algorithm. And I'm being generic here because this applies generically to lots of EAs. On Tuesday, we'll start talking about specifically the GA. So we've got our effectiveness of our EA, that's this axis. And then we've got our selective pressure. So with high population diversity, you have high selective pressure. So that's this kind of axis here. Now, what we've got here is that there is a natural shift toward lower diversity. So if you start with high selective pressure, then you are going to very quickly purge, like all of those low fitness solutions, they're going to be gone. And you're going to be left with only moderate to high fitness solutions. So very quickly, you reduce your selective pressure. But eventually, you're going to reduce it so much that, that drift will take over. That's what's over here, this corner over here. And at this point, there's so little genotypic diversity that there's going to be the inability for there to be any fitness diversity. So the little bit of fitness diversity you might have left is going to be so little that any changes to your allele distribution are going to just be due to random chance. So that's what's going on here with drift. Now over here on the right, this is this problem that I kind of described already, where we had an optimization objective that had lots and lots of local minima. And we would like to find this one, but it happened to be that our population got attracted to this pocket here and started fine-tuning in this pocket and never got a chance to get out and search for this one. That's what happens when you have too much selective pressure. You purge diversity when you find the first good thing in a greedy-like way that you don't do any exploration to find qualitatively different solutions that there might be elsewhere in the decision space. But then, of course, on the other side of it, once you're adrift, you get this stagnation where you might want to be down here, but if you just happen to be at a relatively flat but high spot here, selection which should give you a downward force here. It should start minimizing this thing. You lose that downward force. And these three, which are up here on this hill, the hill is so flat that even though there's slight differences in height of these, they don't end up causing the higher one to be selected against and the lower ones to be selected for. And you end up getting random movement among these or a choice of just one of them. So that's kind of stagnation that occurs there. Those are these two problems that you have. So ideally, we would like to, so if we think about it, there's too little diversity on the left, there's too much selective pressure on the right. So ideally, we would like to choose hyperparameters to stay in this region, this middle region right here. So that's the ideal balance between selective pressure and drift. And so when we start talking about the GA on Tuesday, then we're going to talk about those hyperparameters, selection operators, mutation rates, population size, fitness scaling, etc. You could say, Ted, how do I choose these? What's the guidance here? Well, there's so many of them. Maybe you need another heuristic, a hyperheuristic to help you choose these. But at least to get in the ballpark, then this is what should be going on in your head. That if I choose a very large population size, then I reduce the time, I give myself more time in this region. Because with a small population size, I very quickly, the roller coaster goes up the hill and comes right back down and I land and drift. But a very high population size is a high computational cost. So, if I choose the wrong fitness function, I have a high selective pressure. So those are the things like you have to ask yourself, every time you change a hyperparameter of an evolutionary algorithm, what am I doing to the balance between selective pressure and drift? That's how these things work. And I want to end with one last graphic. And this is one you can also download this one from the module. Basically, it's just reminding us next time we're going to start the GA. This is basically, in a nutshell, everything kind of together here, where we've got fitness diversity on the x-axis, genotypic diversity on the y-axis. And there is a drift force, which is constantly moving diagonally to this point here, where you have no fitness diversity and no genotypic diversity. So this is like the headwind that is constantly pushing against you when you're building an evolutionary algorithm. And so that's always pushing in this direction. You introduce mutation to push back. That mutation is going to give you diversity in genotype. It may give you a little diversity in fitness, hopefully it does, but mutation is random. So that's why this isn't quite all the way this way, it's this way. Now, you've also then have selection. Selection is hopefully moving you towards better solutions. But as it does that, it's going to reduce the diversity in fitness and it's going to reduce the diversity in genotypes. So that's why it's also moving this way in drift. So over here, this is the region where the drift barrier, where you're under the drift barrier. So in this region, you basically selection is insignificant. In this region, selection is working, but if you have high diversity, you're exploring the space. And if you have low diversity, you're tuning or exploiting. And so ideally, you start off in this location with high genetic diversity, and you've designed your selection operator and your mutation and everything else so that for your fitness objective, you follow a trajectory that kind of looks like this. It does a healthy amount of exploration, finds pretty much all the coarse grained solutions are out there, does a bit of fine tuning, and then it spends enough time over here before drift that eventually it settles into drift. But at that point, you've fine-tuned enough and you've found a pretty good solution. Now, the one thing that we're going to add in that is not biological is so-called elitism. That is our hack against drift. And so elitism is something that in evolutionary algorithms saves the best solution and it protects it against drift so it can't randomly go away. So if we combine this with elitism, then when we're down here in this region, we'll find a good solution and that good solution gets put away and protected so that we've got that saved. So unlike biology, where that one could get randomly hit by a meteor, it will be in a protected area underground where there is no way that meteor can touch it. And that elitism plus a smart choice of these operators can make for a very effective algorithm. All right, so that's all I've got for you today. I don't want to keep you any longer. Thanks for your patience. And any other questions, feel free to come up. Otherwise, Muddiest Point, concept check this weekend. GA formally on Tuesday.